Hello everyone. Our question for today is the following integral. It is an improper integral which contains a finite product which can be expressed as follows. In order to solve such integral, we first need to see what we can do with this expression which contains n factors in the bottom. First, this is a fraction which contains n irreducible quadratic factors in the bottom. So we can decompose it as follows. As you can see, we have two n unknowns, a1 up to an and b1 up to bn. Of course, this is a lot, and we need to find all of them. To do so, we first find a common denominator, so we multiply each fraction by the missing factor. After that, we will end up with the same denominator on both sides, and I mean this and this, which means we can cancel them, and we are left with the following. 1 equals to what we get at the top, and this is what we get. Now the question is, how can we find all these unknowns? What we usually do in partial fractioning, we start by replacing x by the zeros of the factors we have. For example, if this were, let's say, x squared minus 4 instead of x squared plus 4, then we can replace x by minus 2 and then by 2 so that we can eliminate many terms and end up with simpler equations, which contains less number of unknowns. But the problem here is that all the quadratic factors are irreducible, so there are no real zeros. So what can I do here? The trick is to use complex numbers instead. We start with x equal to I, thus the factor x squared plus 1 becomes I squared plus 1 and I squared equal to negative 1, so it's 0. So all the factors which contain x squared plus 1 are eliminated. We're only going to be left with the first term. So 1 equal, this becomes a1i plus b1. And when we replace x by I here, we will get some constant, which I'm going to call c1 for now, and I'll get back to these constants later. Thus, the first equation we get is this one. We repeat the same thing by replacing x by negative I, and we end up with the following. And this is good, because now we only have two unknowns, which are a1 and b1, and we can easily find them. We solve the system and we end up with this. And what I'm going to prove now is that all the ai's in the equation are going to be zeros. We now repeat the same scenario and replace x by 2i, and this is what we get. We again solve the system and end up with a2 equal to 0 and b2 equal to 1 over c2. We keep going like that, and now we can come up with the general formula for all the ai's and bi's, which is this. Now it is time to see if we can find a general expression for ck. We come back to this expression, and I will start with replacing x by I. We know that a1 is equal to 0. c1 is the product of these factors for x equal to I, which is this expression. Replacing I squared by minus 1, we get this. I will write the numbers 4, 9, etc. up to n squared as numbers to the power of 2, because later on we're gonna generate an explicit expression for the ck using this form, and we got b1. b1 is 1 over c1, and this is the value of b1. We now replace x by 2i in order to find b2, and we get this. We keep going. This is for bn. What we can notice here is that for any term bk, k taking values from 1 up to n, the denominator will be negative k squared plus 1 squared, etc., up to negative k squared plus n squared. But of course, the term negative k squared plus k squared will be skipped. And now we can write the general formula for bk, which is this, and here I will use m instead of k because we already have k as the index of the product. Moreover, the integrand, which is this product, becomes the sum of these fractions, b1 over x squared plus 1 squared, up to bn over x squared plus n squared, and indeed, the integral now becomes solvable. So the integral, which I'm going to call in, can be expressed as the integral of a sum. This is a finite sum, and the integral from 0 up to infinity of any bk over x squared plus k squared dx exists, as you will see in a minute. So there is no issue with interchanging the integral with the finite sum, because we will end up with integrating a finite number of terms, all of them being integrable over the interval 0 plus infinity. Then we can take bk out of the integral, and we end up with this. In order to solve our integral, we have to use this formula. So it's 1 over k arctan of x over k, which is this, and thus we got our final answer. I will do a particular case where n is equal to 4. Let us use the formulas that we derived. So it is equal to pi over 2 times this sum, and we can simply find all the bk's. These are b1 and b2, as well as b3 and b4, and our final answer is pi over 2016. That's all for this video. Thanks for watching, and see you soon.